Today we are going to go through second part of surface water. We will see the SCS method, and then we are going to see how we are going to calculate the abstraction with using this SCS method. The first subsection is SCS method for abstractions. The SCS method is the extended of the Soil Conservation Service. This Soil Conservation Service developed a method for computing abstractions from storm rainfall. The hypothesis of the SCS method is that the ratios of the two actual to the two potential quantities are equal. So FA over S is equal to PE over P minus IA. This is our equation where P is precipitation, where PE is excess precipitation or direct runoff. S is potential maximum retention, which is the filtration. As you remember, retention is taking the soil moisture, right? FA is additional depth of water retained after runoff, which is again infiltration, cumulative infiltration, right? And the last one is IA is initial abstraction before ponding. From the continuity principle, we know that the precipitation is equal to the excess runoff, right? Like direct runoff, sorry, excess rainfall plus abstraction plus the depth of retention. So this all total is equal to precipitation. So input is equal to output. This is the continuity principle. When we combine these two, this P is equal to PE plus IA plus FA and the previous equation, when we combine, we are gonna have this runoff, direct runoff is equal to precipitation minus abstraction square and over precipitation minus abstraction plus maximum retention, which is PE is equal to P minus IA parenthesis square over P minus IA plus S. This is the basic equation for computing the depth of excess rainfall or direct runoff from a storm by the SCS method. From many experiments, the researchers assume one empirical equation, which is IA, abstraction, initial abstraction, is equal to 0.2 the maximum retention S. Okay, so IA is equal to, we are gonna take IA is equal to 0.2 S. When we substitute this equation into previous equation, we are gonna calculate the direct runoff as is equal to P is equal to P minus 0.2 S square P plus 0.8 S, which is maximum retention, potential maximum retention. When P versus PE graph is plotted, that means in the above equation, this P and PE, whenever you give precipitation, you are gonna get this relation with the direct runoff. When we plot this one, we are gonna have this. As you see in this graph, the cumulative rainfall P in inches plotted, cumulative direct runoff in inches again plotted. Then according to the Soil Conservation Service draw all these lines according to soil, and they concluded the curve number, which is the curve number is 1000 over 10 plus the maximum retention. So curve number and maximum retention, potential maximum retention has a relationship, as you see, and that is from 0 to 100 curve number is drawn in PE versus P graph. Okay, when we use these curve numbers and when we try to find the maximum potential maximum retention, we can just manipulate the equation, previous equation. So S is equal to 1000 over curve number minus 10. We have this equation where S is in inches as well. So the curve number shown in figure is for normal condition. So for antecedent moisture conditions, which is shown as AMC2. So for normal condition, we use AMC2. For dry condition is called AMC1, and wet condition is called AMC3, and these are calculated as curve number 1 is equal to 4.2 curve number 2 over 10 minus 0.0858 curve number 2. So we can tabulate it from this curve number. Then we will plug in this equation and we are gonna have curve number 1. And if we want to find the curve number 3, this is equal 23 curve number 2 over 10 plus 0.13 curve number 2. So in the next section we are gonna see all these curve number, how we are gonna tabulate it, and then how we are gonna take it. We are gonna just substitute, and then we are gonna see for wet condition and dry condition. This curve is again, this curve number 2 is for normal condition. Before we go to the curve numbers tabulated form, we need to also tabulate it by the SCS on the basis of soil type and land use. So for this one, there are 4 soil groups: Group A, Group B, Group C, and Group D. Group A is for deep sand, deep loess, and aggregated silts. Group B, shallow loess, sandy loam. And Group C is clay loams, shallow sandy loam, soil low in organic content, and soils usually high in clay. And Group D is for soils that swell significantly when it's wet, and heavy plastic clays and certain saline soils. As you see here, we have A, B, C, D groups, hydrologic soil groups, and we have land use description. According to land use description and soil group, we have curve number stated here. For example, let's say we have cultivated land. Let me put this guy. Okay. Let's say we have cultivated land, and group B, soil group B, we have without conservation treatment, the curve number is 81. With conservation treatment, the curve number is 71, need to be taken. This curve number, as we said, for 2, AMC2, right? AMC2. So these all numbers is for normal condition. Let's say residential area. If the area, this lot size is 1/4 acre, and the average impervious percentage of this acre is 38. So for group C is 83. Curve number, AMC2 curve number, we get it. Okay, we just take it. Or streets and the roads, which is impervious. So for gravel and group A is 76 curve number need to be taken. Okay, let's solve one example. We need to compute the runoff from 5 inches of rainfall on a 1,000-acre watershed. The hydrologic soil group is 50% group B and 50% group C interspersed throughout the watershed. Antecedent moisture condition 2 is assumed, which is normal condition is assumed. The land use is 40% residential area, that is 30% impervious. 12% residential area, that is 65% impervious. 18% paved roads with curbs and storm sewers. 16% open land with 50% fair grass cover and 50% good grass cover. 14% parking lots, plazas, schools, and so on, all impervious. So this is the land use. So we are gonna calculate right now the direct runoff from 5 inches and of rainfall for the 1,000 acre of area of watershed. For our question, we are going to use the AMC2 curve number tabulation table. And as we see here, I already plugged our question is this guy, and let's write the table so in order to solve better, right? So we have land use here, and we know that the percentage of this, how much we use, and what is our curve number we are gonna put, and we are gonna product it, the percentage and curve number product. Let's say percentage multiplied by curve number. Okay, this is for like soil group. We have B. Let's write here, like, where is it? Yeah. Okay, group B for this one, and then we are gonna have the same thing, percentage curve number, and let's multiply these two parameters, and group C. So we have group B and group C. Let's write it in this form. Okay, so first thing is land use. We have 40% residential area. Also, we need to concentrate here. Group B is 50% group B, 50% group C. So we need to divide it into two. So 20% residential area is for group B, and 20% group C for residential area, that is 30% impervious. So let's write here the land use is residential area, that is 30% impervious. Okay, so writing here. Okay, so what is its percentage? Is 20% for the group B, 20%, half and half, 20% for the group C. What is curve number for residential area? 30% impervious. Let's go to here, residential area, 30% for the 30% impervious, and the average lot size is 1/3 acre. So let's go to just like group B is 72 curve number and group C is 81. So let's write it there, 72 for group CN and 81 group C, and this is the product, so it's equal to this guy multiply this guy, and for here is gonna be this guy multiply this guy is gonna give our product. And the second one is residential area again, but here let's do here is instead of 30 is 65% impervious. So we will go back again our table. Let's go back our table for 65, group B 85, group C 90, and we just need to put 85 for group B and 90 for group C, and we see that is 12%, so 6% is here and 6% for here. Then just need to do this guy in order to make the product, right? Okay, let's fill it out, and then after that we can calculate the product. 18% paved roads, so it's gonna be 9% here, 9% here. 16%, so it's gonna be 8% here, 8% for group C, and 14% is 7% here, 7% here. And then let's go to 18% paved roads, 18% paved roads with curbs and storm sewers. Paved with curbs and storm sewers, 98, 98, both of them is 98, so we are gonna plug here 98 here and 98 here. Let's write it down here too. Paved roads with curbs and storm sewers. The other one is open land, 50% fair grass cover and 50% good grass cover. So let's first of all fair grass cover, then we can go to here in again open, but instead of fair right now we need to write good cover, right? Because it's too different, so it's gonna be instead of 8% we need to make it 4% here and 4% here, then after that 7% here. 4%, 4%, 7%, because it was 16%, so 8% for 50% fair grass, so half of them fair grass, and half of this one fair grass, half is group B and half is group C. And we need to go to open land and fair grass, open land, fair grass is 69, 79, 69, 69 here, and 79 here. Then for good one, good condition, 61, 74, 61 and 74 here. Then the last one is parking lots, parking lots, plazas, school, and so on. So it's all impervious. Parking lots, here there is parking lots and blah blah. So it's 98 also. So here 98%, 98 curve number, 98 curve number. Then let's see the product and see the product. Then let's make the total number of these products. And we also, when you make the percentage addition is 50%, so it's 50%. So we have the 100% of the land usage curve number we calculated. Then right now let's when everything is done, let's do this one. When everything is done, let's see. Okay. When everything is done, let's go to calculated our weighted curve number, and we can solve this question. All right, we know that we can calculate it first the curve number. The what is our curve number? We need to find the, because we calculated the percentage 50%. 50% is group B, right? Group B, and 50% is group C. So we need to make it the average, the also called weighted, because maybe it may be like change 40%, 60% or 30%, blah blah. So we need to find curve number, but weighted curve number, which is as we calculated here, the 4038, right, and 4340. So 4038 plus 4340 over 100, because we made it with product 50% of the curve number cost 4038. The other 50% is 4340. When we divide it 100%, our weighted curve number is 83.8. The average of this watershed's curve number is 83.8, we can call it. Then we can calculate the potential maximum retention as, which is, we know the formula of 1000 over the curve number minus 10, right? We know that the curve number is right now is, let's say, 83.8 minus 10. So we can calculate it as, we can calculate it, the potential retention, maximum retention is 1.93 inch. So this is the maximum retention number. Okay, let's go to the direct runoff calculation. As we developed, the direct runoff is equal to, open parenthesis, the precipitation in this question is 5 inch, right, minus 0.2 s square over we have precipitation again plus 0.8 s. Okay, so for precipitation we need to put 5 minus 0.2 multiplied by, what did we find? 1.93. 1.93. These whole numbers taken square. Then after that we need to divide 5 plus 0.8 multiplied by the S number, which is 1.93 inch. Then after this calculation we can find our direct runoff is 3.25 inch of water. That excess rainfall, which means if in this area, which is 83.8 curve number land, almost you guys see there's like curbs and parking lots and plazas, blah blah, right? So 18% is paved roads, and what we have like 30% residential, which is 30% is impervious. There is 12% residential and 65% is impervious. Most of them is impervious, right? In this kind of places, if 5% rain, 5 inches of rainfall comes in this kind of watershed, 3.25 is excess rainfall. It's called excess rainfall or direct runoff. Okay, in this question it's very easy. We just need to see the tabulate form of AMC2, and we need to substitute these numbers to our equations, and we will find our direct runoff as here. So let's solve the same question, which is 5 inches of rainfall and 1000 acre of watershed. We are gonna recompute the runoff for this condition, but there is no more normal condition right now. It is the wet conditions of AMC2 3 are applicable. Okay, in this question, instead of normal condition right now, we are gonna jump to the wet condition. So let's open our pen again. The curve number 3 we need to use, which we have the equation of 23 curve number 2 over 10 plus 0.13 curve number 2. So we already know our curve number 2 from previous question, which is 83.8. So 23 multiplied by curve number 2, 83.8 over 10 plus 0.13, again let's do in parentheses, and is 83.38, sorry, 83.8, which is curve number 2. When we calculate this guy, we are gonna have, for the wet condition, the curve number is gonna be 92.3 as curve number. So as previous question, we will do the same thing, as we are gonna find again maximum potential retention as is equal to 1000 over S, which is in this case 92.3, and we need to subtract from this number from 10, and we will find here as is gonna be 0.83 inch of depth. So when we substitute this number in our direct runoff equation, which was, again, let's write precipitation minus 0.2 s square over precipitation plus 0.8 s, we are gonna find precipitation, we know that is 5 inch minus 0.2 multiplied by 0.83, sorry, 0.83, all of them square over precipitation, which is 5 plus 0.8 multiplied by 0.83. And this, when we calculated this direct runoff or excess rainfall in wet condition, is gonna be 4.13 inch. Why? Because we know that this kind of soil is almost saturated, so the ponding is gonna occur very fast. Then the 5 inch of rainfalls, like 0.87 inch, is gonna infiltrate it, but 4.13 inch of this rain is gonna be excess rainfall. We also direct runoff is gonna be flow away from the watershed. Next subsection is the urbanization effect. During the past 30 years, hydrologists have paid attention to the effects of urbanization. In general, the flood is concerned in a watershed. The major changes in flow rates in urban watersheds are due to the volume of water available for runoff increases because of the increased impervious cover. Like here, the streets and parking lots, these impervious lands is covered in with the urbanization, so it's affected our watershed flow rates, right? And then change in hydraulic efficiency associated with artificial channels, curbing. Curbing is an example of here, curbing, and gutters is example of here. We have gutters, and storm drainage, as we usually see on the street here. This collection system increase the velocity of flow. So the flow is here, and from the roof to carry all the water, all the rainfall, and as you see here, the curb, there is impervious region here. It's taken the grass area, infiltration, they cut the infiltration, so all these effects making the ponding occurs here or go through the channels, like here, the artificial channels, so increase the flow rate, and then this becomes a flooding problem, or like any other civil engineering problem due to the water. Let's solve an example so we can compare the urbanization effect by non-urbanization, like rural area. Calculate the runoff from 5 inches of rainfall on an 1,000 acre watershed. Same condition. The soil is 50% group B and 50% group C is again same soil group. Assume antecedent moisture condition to the first example is the same thing, right? The land used is open land with fair grass cover before urbanization. So this is before urbanization. Then after that, after urbanization, it is as specified in example, previous example, how much additional runoff is caused by urbanization. So we are gonna calculate how much additional runoff is caused by urbanization with impervious land use. Alright, in this question, we need to calculate it again because the curve number, because it says instead of the previous example, the land use is open land with fair grass is 50% group B, 50% group C. So let's go back to our previous question, the tabulated form of this hydrologic soil group. So it's gonna be open source, open spaces, and fair condition. Group B is 69, group C is 79. So again, let's go back. So group B is 69 and group C is 79. So it's 50-50, right? 50-50. So it's gonna be average of this one. So 69 plus 79 over 2. So the average of these guys. Or you guys need to just multiply 69 multiply 50 plus 79 multiply 50 over 100. Same thing. So when we do this one, we will find is the average curve number of this kind of soil or watershed is 74. Then we are gonna calculate it as we know 1000 over curve number, which is 74 in our case, minus 10. And so as we can calculate it to 3.51 inch of potential maximum retention. And our direct runoff can be calculated from here for 5 inch of rain minus 0.2 multiplied by 3.51, which is S, the parenthesis, all these numbers square over the precipitation, which is 5 plus 0.8 of S. So it's gonna be 3.51. When we multiply, we will see the direct runoff is gonna be 2.37 inch. Okay, 2.37 inch. This is before urbanization. Okay, so when it is the open land with fair grass cover, the direct runoff happens in this group B and group C, 50% group B and 50% group C soil. Direct runoff ours is 2.37 in normal condition, AMC2. Previous example, we take it was 3.25. The first example, we see that it was 3.25 after urbanization. So this is after urbanization. This is before urbanization. So let's go to new pages and let's see over here. Let me see, because I will use this one. So 3.25 25 inch minus 2.37 is gonna be 0.88 inch of water is additional runoff after urbanization occurs, which is almost 27% of increase runoff. That means the flooding occurs 27% more than previous land, which is fair grass cover of open land. So we already solved this question, and let's move on. The next chapter is we need to extend our knowledge. So time distribution of SCS abstractions. Till this point, we only calculated the depth of excess rainfall during a storm. So we didn't have time limit. By extension of the method, the time distribution of abstractions FA within a storm can be found. Manipulating the above equation for FA yields to, so we know that before how we can calculate PE, right? So when we manipulate it, FA is equal to the S parenthesis P minus IA over P minus IA plus S, which here the precipitation is bigger than initial abstraction. Differentiating this equation, the FA over dt, the retention with respect to time derivative is equal to S square dp dt over P minus IA plus S square. So here the only changing by time is precipitation. We are gonna take S and IA as constant. By using this equation knowledge, let's solve example so we will understand better. Storm rainfall occurred on a watershed as shown in column 2 of this table. The value of current number is 80 and AMC2 applies. Calculate the cumulative abstractions and the excess rainfall hyetograph. As you see in the table, the time is given with hours, and each hour is gonna given the cumulative rainfall, which is precipitation in inch. So the initial is 0, the first time is 0.2, the second time 0.9, the third hour is 1.27, fourth time is 231 till the 7th hour, which is the cumulative rainfall is 5.36 inch of rain occurred. So we are going to calculate the cumulative abstractions and excess rainfall or the direct runoff from here. Okay, in this question I already plugged the table here, and then I just write it down, all time and cumulative rainfall. So I just write the first and the second column of this table on my Excel table. Right now I need to calculate the initial cumulative abstraction, okay, which is IA, right? IA I need to calculate. I am gonna calculate this one. We know that IA is equal to 0.2, the maximum potential maximum retention. So let's write it down here. So we know that curve number is 80. It's given in our question. And for IA is 0.2 S. So I need to find this S. S, we know that is 1000 over curve number minus 10, right? Curve number is 80. Let's write it here. Minus 10, which is, when we calculate it, this number is 2.5 inch. So IA, the initial obstruction, is 0.2. This is multiplied by 2.5 is gonna be 0.5 inch. So initial obstruction is 0.5 inch. And when we go back to our initial cumulative obstruction, the first one is 0. Then when it's cumulative rainfall is 0.2, it's gonna be 0.2. It's gonna be same because it's not over 0.5. Then here 0.9, so I need to plug here. Right now 0.5. Then the rest is gonna be 0.5 because the initial obstruction is satisfied, okay, provided. So here retention depth, which is FA, we need to calculate the FA. So it is this guy minus this guy, right? So it's gonna be cumulative rainfall minus initial obstruction is gonna give us the retention depth. So this is also inch, but this both is inch. So we find that is gonna be, sorry, till here is fine, but then after that we need to use here FA formulation, which is S minus, let me write it down here. From here we need to write it down, not the cumulative retention, is FA is equal to S precipitation minus initial obstruction over precipitation, which is 5 inch. We know that, right? In this case, no, the precipitation is given. Let me check the. Okay. So the precipitation minus 0. Initial obstruction. The cumulative, the P is given, cumulative rainfall is given in the table. We know that. Plus S. Okay. So when we calculate here, S is calculated is 2.5 inch is constant. So let's modify this equation. So we are gonna write it in Excel. FA is equal to S is 2.5, right? 2.5. P is the first column, the second column, minus initial obstruction, which we found the third column, over P minus initial obstruction plus 2.5. Okay, so let's write it down, this one in Excel in here, right? Because after the cumulative rainfall is bigger than initial obstruction, it will obey. So okay, 2.5 multiply cumulative rainfall minus initial obstruction over, open a parenthesis, principal cumulative rainfall minus initial obstruction plus 0.5. So 0.34, and just scroll down and we can find our retention depth, which is F, so F subscript A, and this one is I subscript A. So both of the variables is defined here. Let's continue. Right now, what we need to find? We need to find the cumulative obstructions, right? So we need to find cumulative excess rainfall. So cumulative excess rainfall, which is in our case PE, right? We know that from the continuity equation, let's write it here, PE is equal to precipitation minus initial obstruction, right? Initial obstruction minus retention, which is FA. Okay, then let's go back to our Excel form. Then we are gonna say precipitation minus initial, cumulative rainfall minus initial obstruction minus retention depth. So it's 0, we know that this is, and 0 0. Then we will have 0.55, then 0.18, and then 0.76, and goes on. This is our cumulative excess rainfall, and the question is asking to compute the cumulative obstructions and excess rainfall hydrograph. The last one, excess rainfall hydrograph. So we need to find the between these terms. So it's gonna be 0 and where we are gonna find this one. Okay, it's gonna be is equal to this guy minus this guy, and then let's go down, let's scroll down. So this is our excess rainfall hydrograph, and we already solved this question as well, and we are done. The homework is we are gonna do the same thing, same example, but instead of 50% of group B, let's take it 30% of group B and 70% of group C, okay? And redo example 1, and then bring back to here example 3 and find the difference, how much additional runoff is caused by urbanization. So you need to compare these two. This is your homework, and see you next week.